Here we come to a practical example of the free particle. So in part A, we're given this initial wave function and we need to normalize it. So this is pretty similar to what we've been doing in the past two sections when we were dealing with the infinite square wave and the quantum harmonic oscillator. So the first step is always to normalize the initial wave function. So 1 is going to be equal to the integral from negative infinity to infinity of the absolute value of the initial wave function squared dx. So we can just substitute this expression straight in. I can pull out the constant, so the absolute value of the constant a squared, and then inside I have e to the power of negative 2a times the absolute value of x dx. So I can take away the outer absolute value sign because e to the power of something, this whole term is always positive, so it would be redundant to keep the absolute value sign. And if you observe this function over here, you'll see that it actually looks something like this. So this is the x-axis, and this is the axis for e to the power of negative 2a absolute value of x. You see that this is actually symmetrical. So it's going to go up, and then it's going to go down again. So the whole thing, my drawing is not very symmetrical, but the function is symmetrical. So we can do a bit of simplification. So instead of integrating from negative infinity to infinity, so instead of integrating throughout this whole region from negative infinity to infinity, I can just put a 2 over here and then integrate it from 0 to infinity. So I'm only integrating from 0 all the way to infinity. And then I multiply by 2 to count for the other side as well. And because this whole thing is symmetrical, I can just integrate one side and then multiply by 2. And then now that we're going from 0 to positive infinity, x is always positive. So that's why I can take away the absolute value sign. So now we come to this function that should be pretty easy to integrate. So you see why I took away I used this symmetrical property to put this 2 over here and to make the range go from 0 to infinity. So the reason was to get rid of the absolute value sign, because if this went from negative infinity to 0, this is going to give us a bit of complications. So now that it's going from 0 to positive infinity, x is always positive, so now I can take away the absolute value sign. So integrating this, we just retain this term and then divide this by negative 2a. And then we substitute in 0 to infinity. So move on to the next page. So we have, so remember the left-hand side is 1, and on the right-hand side we have the absolute value squared of the constant times 2. And then now we substitute infinity into x. So e to the power of negative infinity. So this is going to be 0. And then when you substitute 0, you get e to the power of 0, that's just equal to 1. So you get 0 minus 1 divided by negative 2a. So in the end you get 2 times 1 over 2a. So the 2's cancel out. So the absolute value of a squared is equal to a. So now we know that the absolute value square of a is equal to small a. But we still don't know what exactly a should be. So it could be anything. This could be a complex number, but we can choose the simplest form for a. So we can just, instead of having this capital A be a complex number, we can just choose it to be the simplest form, to be just a single real number, the square root of a. So any complex number that satisfies this condition is applicable. So we're going to choose the simplest case where where capital A is just equal to the square root of small a. So that means under this choice, our wave function, our initial wave function, is equal to the square root of a times e to the power of negative a times the absolute value of x. So this is how you normalize the initial wave function.